call and approve of the title change?
I'm sure you would.
Yeah, the next speaker is Sebastian.
Okay, thank you. All right, so I augmented the title slightly because I guess these days you have to think big. And climate is everywhere, so that's a new title on this little extension. So we're going to start with the big picture and then move to something more refined. So I basically want to discuss a very or relatively simple setting, how oscillations arise in atmospheric fluid dynamics, and various theories and approximations they have given rise to, and how it fits into sort of today numerical weather forecasts. And then, so this will be the first or the second part here, and I will basically do all this for the shallow water equations because that's sort of the simple system that sort of makes sense. And then I will actually put all this into a very simple framework. It's almost trivial. I will consider a single particle in a fluid and how it oscillates, so to speak. And we'll look at the various theories in that context. And then in the last bit, we will not quite get back to the complete PDE limit, but sort of trying to go back to the continuum limit of infinitely many particles, and then you essentially back to the shallow water equations again and appropriate theories. Okay, so the first thing that, since we're here at a highly oscillatory workshop, this program, of course, highly oscillatory doesn't make any sense if you don't talk about slow stuff as well. So you definitely need sort of a reference scale, and for PDEs it's a length scale and a time scale. And if you look at all the things that go on in the atmosphere, you have all sort of things. The real interesting things for meteorological interest are along these lines, essentially, sort of cloud type things, thunderstorms, fronts, and then large-scale cyclones, etc. And then there's also things that you're typically not interested in, like sound waves, but of course they're part of the equations. Then here you have, for example, small-scale turbulence. So if you were around an airport, you were predict circulation patterns around, or you wouldn't call it circulation, just airflow also around the airport. That would suddenly be of your interest. So this would be, even though in the big picture that's very fast, then actually it's no longer fast. So, but for sort of daily forecast or prolonged forecast, the typical time scale that's of interest is of course in the range of days, which is here, or hours. So we're talking about this here, and the scales are in the range of kilometers or hundreds of kilometers, so you're somewhere here. So essentially, this part of this picture up here would be slow, and everything else in the model is sort of fast, or of short wavelengths, either fast or short wavelengths. So this is really to be resolved, this picture up here. And everything else is would be highly oscillatory or very short wavelengths. Now, in terms of large-scale horizontal atmospheric motion, and most of it is because the motion is essentially horizontal. Of course, there's vertical convection going on, but that's already more small-scale stuff. So the large-scale patterns are largely dominated by horizontal motion. The reference scales that make sense are given by the rate of the rotations or angular velocity of the Earth, or more precisely, if you are somewhere in mid-latitude where we are, then you have to appropriately scale this, the local angular velocity of the Earth at your point where you are. And the natural length scale is also given, given by the radius, Rossby radius of deformation, which is the ratio of the gravitational constant times the height of the layer, which is typically taking 10 kilometers, square root of that and divided by f. So that gives you a dimension of length. And that's sort of a natural reference length scale. So once you've given your reference scales, you can sort of conduct an experiment and think of everything. Of course, your model has fast and slow stuff both, right? Included. But you can think of a subset of the space of all solutions which doesn't have any fast solution components, and then you would call that subset, manifold. Of course, we don't know really the structure of that set. And because it only has, you sort of look at the solutions that are not highly oscillatory or don't have highly oscillatory components, then this is sort of the vague concept of a slow manifold. And that's a very important concept in metrology. And it comes up in two ways. Either you explicitly reduce the equation, so you project your equations down somehow. If once you know what this slow manifold is, a subset of phase space, then you could think of projecting the equations down on that manifold, and that's called filtering in the metrology, or we would call it reduced model reduction, right? Of course, the problem is that in general we don't know what this manifold really is, but we will go through it for a few examples, for one particular example. Or what is now much more common in metrology is to actually say, well, we're not going to reduce the equations. We work with the full equations, which have all type of solutions in it, the highly oscillatory and the slowly varying components. But we choose initial conditions so that the oscillations are not excited. And then your hope essentially is that you start on this set, and you hope you will stay close to that set. So that's, if you have some adiabatic concept behind, you can then maybe argue that this is a reasonable assumption. Of course, that's not clear either. So, but that's what's essentially done these days. So in numerical weather forecast, you work with the full equations. You do as little approximations as absolutely necessary, but you carefully initialize your code and then run it with a time step that is certainly large compared to the oscillations that are hopefully not excited. So you're not resolving any oscillation that would arise.
Sorry, Sebastian,
yeah.
But in forecasting, you're given your initial conditions, right? So you seek something nearby on this slow manifold or something?
Well, the thing in numerical weather prediction, actually, the initial conditions are not given. They're observational data, which are data which is much less than you need to actually initialize your numerical code. So it's all part of a huge process called data assimilation. So you have observational data, you have the last forecast, and you somehow mix it all together, and you try to get an estimate for the current state of the atmosphere.
And then on this slow manifold.
And then you try to project it down, say to say that it's on that slow manifold. I will come back to this. I mean, also in some historical comments. But yes, that's basically what you try. So this becomes part of the data assimilation that you filter your initial conditions, but you don't filter the equations themselves. Okay, so it becomes all. I mean, it's all much easier if you look at some equations. So in the, I've been talking about this now for a number of years, so most of you have seen those now. Shallow water equations, a single layer. Do you think of the atmosphere, a single layer, no vertical motion, so we just averaged out all the vertical components, so it's entirely horizontal motion of a fluid. So this is the horizontal velocity field, the u component, the v component. This is acceleration, so this is the material time derivative. So it's the partial time derivative plus the usual advection terms. This is the Coriolis term that comes from the rotation of the Earth, and here you have g times pressure gradient, so to speak. But in the shallow water equations, the pressure is actually just given by the layer depth gradient, or the gradient, the layer depths. And the layer depth in itself is satisfies a continuity equation. Right. So these are the simplest model that one can work with. It has some interesting features. Now, as I said, to talk about fast and slow and all this long length scales, short length scales, you have to look everything with respect to a reference scale. So the reference scale already introduced. So this is this 1 over f, the Earth rotation rate, and the ratio of the time scale of interest you look at to this reference length is called the Rossby number. We will see that we typically assume that this is small. So we assume that we look at time scales that are long with respect to one rotation of the Earth. So 1 day, essentially. So you look at things that evolve over several days. So really large-scale patterns, right? And the other ratio you have is the Rossby deformation radius to the length scale of the phenomena you're interested in. And the square of that is called the Berger number. So again, you're looking at phenomena that are large with respect to this Rossby deformation radius. And then the Berger number will be small. So I will now sort of go through and roughly first, in the first go, will roughly motivate to you one of the very common models, reduced filtered models, that is it is in use in meteorology and has been actually successfully used in particular in the theoretical understanding what's going on in the atmosphere. And it's called the semi-geostrophic theory. And it's basically looking at the limit where both the Rossby number and the Berger number go to 0. And for simplicity, we use Rossby and Berger number equal to epsilon. And then if you go back, you see this is a ratio of equal to 1, and you end up with something that's a small number multiplying the acceleration term. And then here you have 2 terms of order 1, 2 terms of order 1. Nothing happens down here. And you can already guess maybe what happens then. You say we decompose the velocity field, which is really the wind in physical terms, into, well, we still have to, I mean, I call it now slow, but of course that needs to be justified. But we call it we formally decompose it into a geostrophic part and an oscillatory, again, we have to justify that's actually oscillatory, ageostrophic contribution. And the geostrophic part is just given by saying that if that's a smooth solution, I mean, this is of order 1, this derivative, then this is a small number, so that requires that these two things, well, if they are of order 1, then they should be in balance, right? And that's exactly the definition of a geostrophic velocity, that that these two terms are made equal and the same for the second equation. So that gives the definition of the geostrophic wind components. And essentially then you're left with the ageostrophic part, and that's the one that rapidly oscillates. So you can basically think of what's happening in the Rossby, in the semi-geostrophic limit. You have a rapidly rotating velocity field spinning around, and there's a slow systematic motion, which is the geostrophic wind, right? So this is where the highly oscillatory bit comes in, and that's where the sort of slow part comes in that particular scaling limit. Of course, initially, the meteorology community said, well, we can completely ignore the ageostrophic part. We just set that equal to 0, and we use this as a filtered equation. That's the quasi-geostrophic approximation. We'll come back to this in a minute. But in fact, a much better approximation is to say, well, we don't, we basically just ignore the acceleration part of the acheistrophic component. And we then change the shallow water equations just by saying that we leave everything as it is. We just here in these two places we replace the true velocity field, which is slow and fast combined, just by the slow geostrophic part. And that's what gives rise to the, at least the meteorology community, quite celebrated semi-geostrophic equations. At this point, of course, this is quite mysterious. I mean, why you're doing this, how it is really is reasonable. Also, it's not clear what the mathematical properties of these equations are. Like, are they still Hamiltonian? I mean, we started from, I didn't say that, but I mean, the shallow water equations are conservative. There's an energy conservation. There's various symmetry properties. So it's not clear at all what these equations, what the properties of these equations are. However, it was essentially Hoskins that introduced a quite intriguing coordinate transformation and looked at the equations in this transformed coordinate system and then revealed that there's actually quite a lot of structure. Okay, so this is a very rough wrap-up of sort of the mathematics, and I will try to sort of make a bit more transparent when we go to the single particle approximation. And then everything becomes actually almost trivial. Anyway, maybe of interest also to give a bit of historic perspective. So I already mentioned the quasi-geostrophic model, which basically says that you completely ignore all the ageostrophic solution components. So you just work with this geostrophic wind, which I defined before. That's exactly the same. So you're basically saying that here's a quantity Q, and I transport this by just saying the velocity field or the wind is just a geostrophic wind. So you completely ignore any geostrophic component. And this particular quantity we choose is called potential vorticity, and it's given by this. Now, PV is a materially conserved quantity for the shallow water equations. So we keep this property in this approximation, the quasi-geostrophic approximation. And so also here is again just a geostrophic wind in there. And this, in fact, is a closed system of equations. And one has to look at it a bit, but that's relatively easy to see. Now, this equation was proposed, that's at least my understanding, in 1938 by Rossby. And he used it to explain some sort of wave phenomena in the atmosphere. Essentially, if you have the jet stream, it starts meandering, and it breaks up in cyclones. And that sort of instability that gives rise to cyclones he discussed in this sort of simplified setting. And I guess he did that successfully, so it really explains, at least in a conceptual way, how this sort of the jet stream breaks up occasionally into cyclones, anticyclones, etc. More interestingly, Charney in 1948 basically said, well, this model is actually suitable for global atmospheric circulation simulations. And in 1950, Neumann, Fjordhoft, and Charney again, they conducted the first rather successful quotation mark weather forecast using this simple model on the ENIAC. So that was basically following the lines that you try to as much simplify your original system. I mean, it's a tremendous simplification to saying the atmosphere is given by this set of equations. So, I mean, it's just actually almost unbelievable that this gives anything reasonable. And because you simplify the equations dramatically, then you can use numerical techniques to make it work. Sort of on a different line, Hinkelmann in Germany, he actually wrote a paper, the mechanism of meteorological noise. I always like this meteorologischer Lärm. In 1951, he actually sort of one of the early works at least suggested, don't do this, work with the full equations, and instead using this initialization idea that you choose appropriate initial conditions, but then you don't use reduced models. Then in 1959, he showed that this can actually be all made to work, And it was put into operational use by the German Met Office actually in '66 as the first Met Office that ever used sort of the full unapproximated equations. There are still some approximations in the primitive equations, but relatively minor. Interesting, you might have heard of Richardson, who in, I think actually 1918 or something. The book was published in 1922. He was bold enough to do a hand calculation forecast for the weather. He was the first to really say that you can actually do numerical weather forecast by the equations proposed by Berknes in the early 1902 or so. He actually also worked with the primitive equations. So he didn't use any of these equations. So he knew only, the primitive equations. And the forecast was a spectacular failure. The failure was basically because he didn't initialize the data correctly. So he had lots of noise. He had this lärm in his calculation. So the pressure fields were way out. But it was really just because he didn't initialize. He had too few data points, and he had to fix it to the mesh, or extrapolate to the mesh, or interpolate, and it was just too noisy. Sometimes it's claimed that he didn't know about stability, so that his scheme was actually unstable. That's actually not true. You can actually download Peter Lynch on his webpage. He has a MATLAB code. You can repeat a Richardson experiment, and you can also now repeat the ENIAC. Just a simple MATLAB code. You can repeat these simulations. It's good fun. Okay, so more recently, Hoskins in 1975, he really introduced the semi-geostrophic equation, which I stated before, so this sort of improved variant. And the reason was really that you were unable to produce frontogenesis, to explain frontogenesis using the quasi-geostrophic equation. Basically, you couldn't get the very rapid formation of fronts that sort of just can happen over a few hours or just in the course of a day. So the quasi-geostrophic approximation wasn't able to do this, but using the semi-geostrophic equations, he got that. And at that point, he also introduced the Hoskins transformation. Now then, later on, Mike Cullen and Purser sort of revealed the geometric structure. It's linked to optimal transport problems. We will have a workshop this summer in Edinburgh on this. It's quite fascinating, all the sort of geometry that comes into these quite innocent-looking equations. Well, on a different line, Browning and Kreis. Kreis was meant to be here. Unfortunately, is not coming, I suppose. Sort of introduced a systematic study of scaling regimes by a derivative principle. Rick Salmon looked at the sort of Hamiltonian variational side of the semi-geostrophic equations and tried to derive higher order approximations. So basically saying, well, we have one definition of, you have sort of one approximation to the slow manifold. You would like to extend it order by order, right? There's a small epsilon. You could argue, well, you would like to get this to arbitrary high order. So he tried this. And then there's a very funny sequence of papers by Edward Lorenz. This is a famous Lorenz, right? The chaotic chaos Lorenz. He first wrote a paper on the existence, 86, and then the following year on the non-existence, 87, on slow manifolds, right? Of course, we basically now also know that even if in the best of all settings, for Hamiltonian systems, you don't have a slow manifold. In the exact slow manifold, there's always, in general, there's a non-existence. And then there are lots of recent work. Michael McIntyre here at DAMP did a lot of work recently. Marcel Oliver, Giaco, Mike, and also Ian Ralston. And actually, Ian, for example, is at the moment very interested in linking SG with data assimilation. Okay, so much for the historical comments. So now, let's explain what's really going on for the single fluid picture, single particle. It's embarrassingly simple. So instead of investigating the full shallow water equations, we're going to just consider the following simple model, where basically all we're doing is to say the fluid, the layer depth, is, of course, in the shallow water equations, a dynamic quantity, so it really evolves in time. Let's just say we know this for a moment. This is a given quantity as a function of time and position. In fact, that's something not so outrageous. If you go to the ECMWF webpage, you can download this information from the last 40 years, called it last 40-year reanalysis or so. I mean, you can get this data for realistic from realistic simulations. So you just take this. I mean, you assume that this is known to you, and then you say, well, what happens if I have this and then just evolve? Look what the single fluid parcel would do. And it's essentially, this is now becoming a potential, right? So this is Newtonian equations of motion for a single particle in R2 under the influence of a given potential. And the only difference to what Christian was talking about earlier is that now you have here, due to the Coriolis term, you have a velocity-dependent term, force. Okay, so we do a bit of modeling around. So we change time, and we introduce momenta to make it sort of first order, and then you get this system. So entirely trivial, and it can be put into this frame, and now no, not yet, but I will in a moment also assume that now basically saying this is really a potential. So this I call V. And I drop for the moment time. It's not essentially, I mean, I could have left time here, but then energy is not conserved. It's actually not essential. So it's a Hamiltonian system with a slightly modified structure matrix. So in general, you would have here a zero block as well. So it's a 4x4 matrix, identity minus identity, and the term that comes from the Coriolis force. And the energy is just kinetic plus potential energy, kinetic energy, potential energy. Everything is in R4. All easy. So then you have the dual picture. You can go to the Lagrangian framework. So you write everything as a second order differential equation again. You can either view this as the Euler-Lagrange equations with this regular sort of Lagrangian density. So this would be the maybe more intuitive view to immediately get there. But it makes also a lot of sense to look at this degenerate Lagrangian and still keep the momenta p. So if you derive the equations of motion, you would take variations with respect to q and p, but you get exactly, I mean, after eliminating p, eventually you end up with the same equation. So you have different Lagrangian functionals, and they give you the same equations. This is nice because this is the Hamiltonian I just stated here. So this is kinetic energy plus potential energy. So it converts the Hamiltonian picture more easily into the Lagrangian picture. Okay, so I already mentioned that Rick Salmon did work on trying to understand the semi-geostrophic equation in this context of variational or Lagrangian formulations, and also to get from there to higher order approximations. So basically, the idea is quite simple. Instead of doing it, doing the approximation right on the level of equations as we've done at the very beginning, you now do it on the Lagrangian level. So basically everywhere where you have a p here, or here, and here, you replace it by the geostrophic value. So p is no longer a quantity you can take variations independently, but it's sort of now a slaved variable. And then you look at your Lagrangian, you might order terms according to powers of epsilon. And now another crucial thing comes in. To simplify the equations, you also introduce a coordinate transformation. So you're basically saying I'm shifting the perspective by going to a slightly different coordinate system. to simplify the equations. And the transformation is again expanded in powers of epsilon. And the first non-trivial term is given in this by this here. And we keep lambda as a free parameter for the time being. And then you plug it all in, and you collect terms, and you throw everything away that's of order epsilon to the 3, and you end up with this system. So with this Lagrangian in the new coordinates, using also the quasi-geostrophic replacement of momenta. And so what you get is this is basically giving rise to Coriolis term. This is the original potential energy. Then you end up with a new term, which is sort of a correction, which you can think of a force, because it just eventually will give rise to a force, because that's just the position dependent. And then you have another of these mixed terms, which is actually a bit nasty looking. So the natural inclination is, there are actually, I guess there are two natural choices of lambda to simplify the equation. You can either say I make lambda equal to 0, then this term this term drops out, but this somewhat nasty term will remain. Or you say, okay, lambda, I set it minus a half, and then this term drops out, but you need this. It seems that this is a better choice. So in fact, we choose lambda a half. And then you get indeed this transformation to leading order actually becomes the Hoskins transformation. So it pops out quite naturally. And the equations of motion are also quite simple. This is skew-symmetric matrix. Remember, this is 0, minus 1, 1, 0. That's a skew-symmetric matrix multiplying the derivative of q. And then on here you have basically the gradient of now augmented potential. And so these equations are actually Hamiltonian now, right? In Q, canonical. I mean, basically you split Q in the x and the y component. And yes. And what's written here is actually your Hamiltonian. This is then the Hamiltonian. Now this is clearly now only first order, so it's clearly a reduced model. So all the fast waves are gone. I mean, this is even, in dimensions, it's no lower order. When you start with R4, and now we're down to R2, right? The dynamics is now in R2. They can be derived from a Lagrangian functional. These are exactly, if you take the original semi-geostrophic equations, apply the Hoskins transformation, that's exactly what you get. That's why the Hoskins transformation is such a nice transformation, because it converts equations that first have apparently no structure into a Hamiltonian system in the Q variables with a well-defined Hamiltonian. Okay. Now, the messy bit comes in when you now try to generalize this to higher order. I mean, Marcel Oliver, Georg Gottwald have been working on it, Rick Salmon. It becomes rather awkward. The other problem that is with this gives you a set of reduced equations, right? But it doesn't tell you anything if you were to start your full equations slightly off the initial conditions implied by this. Would you stay close to this manifold? What is the dynamics around this sort of slow manifold? That's completely gone. So this is really a filtered set of equations. It has no information what happens away from this slow manifold. And it's also rather difficult to generalize to high order. Now, I mean, most of you probably have guessed what's coming now. All this is sort of much easier if you actually go to the Hamiltonian side. And it's kind of interesting that nobody has looked at it from that perspective, from the geophysical community. So you can basically, you go back from the Lagrangian to the Hamiltonian side and you do normal form theory. And normal form theory is essentially trying to find a transformation that's symplectic, so the equations remain conservative, Hamiltonian, so that the fast and slow variables are entirely separated, well, up to a small remainder term. And because the transformation is all symplectic, you can actually entirely work on the side of Hamiltonians. You never touch an equation, actually. You just look at the Poisson bracket and Hamiltonians. Oops. So what you get is essentially you start with your original Hamiltonian. You apply a coordinate transformation, which is symplectic. That gives you the new Hamiltonian and the transformed coordinates. And you try to do it so that you get the kinetic energy, something that's originally is just the potential energy, but now has more terms in it, and then a remainder term that eventually will truncate, right? That's what you do always. And the key idea is that K and G should commute. So basically, if you ignore this term, you know that the kinetic energy is preserved, and that is also preserved individually. So these become individual sort of adiabatic invariants. And you do this recursively, and you generate the transformation in each step by finding an appropriate Hamiltonian function. So this is a Hamiltonian, the flow of a Hamiltonian differential equation. To find that, you have to solve a homological equation, which is trivial in this case because it's a single frequency system. So there are no issues with resonances or anything. So that can be all done. And what you get is the standard results now just applied to this particular problem. So you can get sort of this slow manifold idea to arbitrary order. And in particular, if you initially start with a geostrophically balanced velocity field plus potentially higher order terms, then you will stay in an epsilon square neighborhood over exponentially long times, provided your layer depth is real analytic, of course, right? So it's a bit tricky. Now this is where the difficulty comes in if you move back to the PDEs. Now you can also think of saying, okay, well, in practice you can't, but as a theoretical idea, you could say, well, I start exactly on the slow manifold. The slow manifold is defined in the transformed variables by setting p equal to 0. Then basically the dynamics on the slow manifold is given by this. And to leading order, the G is then given by exactly the Hamiltonian that appears. I mean, this is now, if you leave this term away, this looks now like semi-geostrophic theory. We had this Q-symmetric matrix multiplying the time derivative of Q, gradient of some Hamiltonian, right? So in G we had was the V, the original potential, plus epsilon, the norm of the gradient of V. That was the next correction. But now you can actually push this to any order. You get the epsilon square, epsilon cubed, etc. correction terms. So, but the leading order terms agree with semi-geostrophic theory. And well, there's always an exponentially small remainder. And also what's maybe expected, but it comes out, is that to leading order, of course, the symplectic change of coordinates reduces, restricted to the slow manifold, to the Hoskins transformation. Of course, here we need more than the Hoskins transformation. The Hoskins transformation just told us how to change coordinates. But here we also transform momenta, right? We work in R4, so we need a more complete transformation. So we need a transformation in Q's and P's. The Hoskins transformation just worked on the Q's. So this sort of the restriction of the complete transformation onto the slow manifold agrees with the Hoskins transformation. And you can do a little experiment, and you see indeed that in a particular setting you get that as I said, I mean, basically what comes out here is that the kinetic energy in the transform coordinate should be preserved up to something exponentially small. And you do so a little experiment similar to what Benetton and Giorgilli did to show this sort of extremely good conservation of energy. You do a similar experiment here, and you get this exponential envelope for the drift in energy. So this is here down is epsilon, so this is larger, this is smaller, and so you have sort of locally you have spikes which sort of due to resonances, but you can bound all this by an exponential. And the red line is because I used the symplectic time scaling. I just wanted to show that the error in energy is well below the error that's introduced through the equations in the finite epsilon effect. Okay. Right. So far so good. I mean, we basically have now, I mean, a very easy, you can give to any student, you can by hand so calculate the first steps of the transformations, etc. Understanding of semi-geostrophic equations. How do we go back to the continuum limit? Well, the first step is actually not so difficult. So we basically now, so far we have assumed that the layer depth is given. Now this is not reasonable, of course, so because mu is a dynamic quantity itself. So I've also worked a lot on particle methods. So the natural first step towards the PDE limit is to actually say that we don't have just a single particle moving around, but we have a whole sequence of particles moving around. And each particle has a mass, and each particle carries a shape function, positive, and the layer depth is the approximation of these lumps of mass moving around. And so then you have actually a dynamic, consistent approximation. You can really show that this satisfies the continuity equation. So this is really an approximation to the time evolution of the layer depths, but from a Lagrangian perspective where you really have particles swirling around. And so you have a finite dimensional model which is still Hamiltonian. This is very nice. And of course, in the way I wrote it, it's actually quite well known as the smooth particle hydrodynamics method. Okay, so then the rest, but it doesn't, so things don't change dramatically. So now this is, for each particle, we still get the sort of same setting, except they now coupled through this potential. And we do exactly the same scaling. Is that we do Berger number and Rossby number of order epsilon. And so you rescale time, and so you get this system of equations. The complete set is Hamiltonian, as I said already. So you want to apply normal form theory to this. Furthermore, to simplify everything, we assume for simplicity that all particles have the same mass. Then the energy looks like this. Kinetic energy plus, now this is potential energy. Now the important observation is that, that as you increase the number of particles, the mass actually goes to zero. I mean, or decreases to the same rate. So actually the product of sigma times n is constant because the total fluid is remaining the same, right? Now, for a long time, this smooth particle hydrodynamics was a bit of a dubious method because there was nothing really theoretically known about it. I mean, there was no convergence analysis. It was used by the physicists, in particular in astrophysical contexts, sometimes in fluid dynamics as well, but it sort of, it was a bit of a, in a rough state theoretically. But there's been quite, it has been largely overlooked paper by Oerschläger, I think, who is in Heidelberg in '91, who showed that SPH for a given basis function, so you don't change the basis function, you just increase the number of particles, converges to a regularized set of shallow water equations. That was actually made a bit more explicit by Delisio and Pulverandi and someone else in 1908. So you actually get to a PDE limit. So keeping this shape function, the support of the shape functions constant, you get the PDE limit. And it's actually, you can think of this being and what do you call it, mu. So, so you get a convolution. So this is the identity for the shallow water equations. If you look at this limit, n to infinity with constant shape functions, you get basically a convolution here operator that is related, of course, to the shape function here. And then the tricky bit is to really prove, and that Oerschläger actually did as well in this paper for the shallow water equations, quite tediously by going through all sort of, it's really sort of manually checking all estimates, that if you then also let the support go to 0, that you, for finite times and provided the initial condition sufficiently regular, you get convergence to solutions of the Euler of the shallow water equations. So it's quite a remarkable. I mean, but that's specifically to the shallow water equations. Okay, so but back to the semi-geostrophy, we now apply basically normal form theory to this system. And of course, the theory goes through for fixed n and epsilon to 0. This is trivial. But the interesting bit is that you can also show that actually increasing n doesn't deteriorate all the constants, or doesn't deteriorate the constants in the estimates. Because, first of all, it's just a single frequency. All the particles spin with the same frequency. That's not quite true anymore if you look at the whole globe, because then, of course, the frequency depends where you are on the sphere. So it would be a case of slowly varying frequency, because it depends where on latitude you are. But if you do the F-plane approximation, which is commonly done for regional models, then F is constant, and then it's a single frequency system, so the estimates don't deteriorate, as first pointed out by, I guess, Pinnerton and Georgili in one of the papers. And but it also doesn't deteriorate. The potential energy estimates don't deteriorate either, because this product remains a constant, which comes from the conservation of total mass. So the estimates formally go through as n goes to infinity. So basically, you could say that all these semi-geostrophic estimates are still true for this sort of regularized set of shallow water equations. Of course, this analysis then collapses as you make the function psi approach the Dirac delta function, because then the analytic estimates just go through the roof. I mean, then you have no control anymore. Then I don't think there's any hope you can extend that normal form approach to the limit psi goes to a Dirac delta function. But basically, from normal form theory, under this assumption that you're willing to work with such an approximate regularized set of equations, implies that there's absolutely no exchange between potential and kinetic energy, which is quite remarkable. So basically, the shallow water system, you can think as a many particle system, like molecular dynamics. So the only one of the remarkable things, because of the rotation, Earth rotation that comes in, this of this Coriolis term, there is no exchange between kinetic and potential energy. Right? Normally in molecular dynamics, you would say the kinetic energy, potential energy can arbitrarily change. But this is not true if you introduce rotation. And that makes the dynamics unique, I think.
Is number 4 necessary to have good approximation of fine scale features?
Well, basically, the psi, the support of psi, actually it relates to your L. So you say you want to resolve a length scale L. it's like, actually the support of that L is like delta x, right? So for a fixed delta x, I would increase the number of particles, and you can show convergence to a set of regularized equations that sort of filter out. I mean, this is sort of an averaging that takes away all the structure that would evolve below delta x. And then, if I then would also want to show delta x to 0, then I would get into troubles, because the derivative of psi, of course, even if you assume it analytic, then you know the Cauchy estimates go through the roof.
So what is the price that you pay if you fix that small? Because obviously in the limit, if it fails in the limit, then near the limit it must be also problematic.
Well, I mean, you have to make epsilon smaller and smaller. Right. But I mean, to be honest, if you talk fluid dynamics, in general, you don't have a global existence theory anyway. I mean, for the Euler equations, it's hopeless, right? I mean, okay, so let's finish with two pictures. So this is this is a many particle simulation with SPH sort of type. I mean, we use a slightly different version of it, but it's where I just plot the dynamics of two particular particles. So, so what happens here? So these two particular particles, well, that's a bit unique actually what happens here. But anyway, so you see that they, it's again sort of a special setup. So initially the geostrophic wind is 0. So they just spiral around. So this is a rapid oscillation. And that the radius sort of gives you the kinetic energy, right? This is related, the radius of this oscillation is related to the kinetic energy of this particle and the kinetic energy in that particle. So then you sort of add the geostrophic wind so they get blown away, actually here, actually quite rapidly, so epsilon is not too small here. And then you stop it again, and you see that they exchanged energy, but the sum of the radius squared, I suppose, is kept the same, right? So particles can exchange kinetic energy amongst each other, but the total kinetic energy will remain the same. And of course, if initially you use balanced data, that would mean the radius, you would try to make that really small. That would be corresponding to the case you start in geostrophic balance initially, so you don't want to have these oscillations. Then, the picture essentially would not change. Just the radii would stay small, which then actually also justifies don't bother, right? Try to initialize the system so that this radius is initially 0, and don't try to actually resolve. I mean, these exchanges of energy are of no physical significance to the large-scale circulation, right? That's why initializing in meteorology appropriately is actually, at least in this context, a very good idea, because no point in resolving these oscillations. And here's, well, that comes through very badly. This is a full simulation. This is a baroclinic instability. So you start with a shear. I've shown it in several of my previous talks, and some of you have seen it, probably these pictures. So basically, you have a shear, and then it breaks up. You get vortices, several vortices. So here you see actually two pairs of vortices forming, and they start spinning around. What you can't quite see, but I tell you, this is the total kinetic energy. It's basically a straight line. So this is saying that total energy is conserved by our method, more or less. So this is down, this is a relative, this is 10 to the 0, this is 10 to the minus something. So the energy is 10 to the minus 6. This is the energy error, so it's very, very small. Kinetic energy in itself is preserved. If I plot the potential energy, it would also be conserved. And what I plotted here is the agiostrophic part of the kinetic energy. That's the kinetic energy that comes from the spinning. So, so here you can see I initialized the data so that this part of the kinetic energy is very small, and it stays very small throughout the simulation. So these oscillations don't get excited. Of course, I didn't use here any sophisticated machinery, so the time stepping actually resolved all the oscillations with very small time steps. So it could potentially be an application of large time step methods. Actually should be rather straightforward to do here in this, I mean, almost trivial, I suppose. to use to combine this with large time step methods and trying to reproduce this behavior. All right, so that's it for today, and the numerical implications we will discuss next week. Thank you.
Thank you. Other questions?
As you pointed out, kind of back to early days, people were trying to filter out these hyperbolic components in PDE systems. But, you know, starting from Smagorinsky's work, basically the hyperbolicity idea came back, and one of the way to improve the system was, as you mentioned, to try to improve initial conditions. But the other way is, you know, atmosphere is not the big picture. Atmosphere is just a small part of the entire picture, because you have to take into account ocean, you have to take into account sea ice, and many other things. So basically, you know, in weather prediction literature, of course, you know that sort of it's a big step towards coupling of different components of the climate: atmosphere, ocean, sea ice, as I mentioned. And then you do not filter those components. And sort of similarly, people moving along that direction pretty heavily. And also another comment, like also you mentioned in terms of this vertical motion. Also in climate literature, it's quite well known that this could contribute quite substantially to overall prediction of climate.
Oh yeah. I mean, there's no doubt. I mean, I use this really as a simplified setting. I mean, people actually using now moving towards non-hydrostatic models. I mean,
Right. So I guess the question, what in the end of the day, what do we get, you know, by filtering out those hyperbolic components? Because it you know, this sort of trend has been around already, as you pointed out, back to early days of climate prediction.
Well, I guess there's this general issue. I mean, if you, I guess, like if you think about moist processes in atmosphere, I mean, not to make it too complicated, not ocean, and I mean, just the moisture is already complicated enough. Of course, there is a big issue what coupling moist physics, which is typically not resolved, it's just a parameterization, how that feeds into the circulation model, and whether that would actually excite modes that you initially try to avoid. Is that sort of along the lines what you were asking, right? Yeah, I think that essentially, I mean, people, when you talk about initialization and this filtering, it's actually not as dramatic as it sounds. It's basically trying to initialize so that there's relatively little noise at the grid resolution, which you're not resolving anyway, whatever. I mean, it's not saying that you're trying to initialize the system so that the solutions are smooth on length scale that are much, much larger than the grid size, delta x. So you're just basically trying to get your initial data so that it's smooth, so that you can resolve it on your numerical grid resolution. Right? So it doesn't make sense that you have, you know, zigzag or something that jumps on the scale of delta x, right?
How do you know that it would reflect the physics?
Well, I guess in these complex models, nobody knows, right?
Well, not if you continue sort of refining the models by the way of coupling of different components of the climate, and that's what people are doing.
Right. Well, I mean, okay. Well, it's of course. I mean, you always. I guess it's a matter of resources, right? I mean, of course, everyone would try to increase the resolution. That's what's happening. I mean, that's the biggest improvement has not come probably from improving the numerics per se, but just that you have bigger computers, you get a higher resolution, you can improve all that sort of, yes. But you will always have to face the fact that at any state in time, you have a certain resolution you can afford to make any reasonable predictions for a week or so. Because if you were going to higher resolution, you would not get there in time to get the forecast out before the weather is here. So then you always have this issue that you somehow have to think, what are the appropriate conditions, initial conditions, given a certain grid resolution. And then it's also, of course, the question, what is the correct physics or a parameterization of physics that also corresponds to that scale. I mean, clouds are the best example, right? So far, clouds are on a size way below the grid resolution on a global model. Now they're getting to the size. I mean, the clouds can almost be resolved, not quite.
Well, but the reason why they do that, because they take into account solar radiation and many other components. Again, it's by the way of coupling of these models, rather than decoupling them and filtering out.
Yeah, no, well, they have always been the practical, I mean, except for the very early days where all the moist processes were completely left out, because they've been in since, I guess, the 70s or whatever. I mean, you always try to get some sort of moisture built in. Actually, the French, I mean, I just read it's kind of hilarious what they do to get, they look at the saturation rates. So they have moisture as a variable, dynamic variable, and then depending on the temperature and pressure, etc., you get the saturation rate. So if it comes above the saturation rate, they're not having any clouds, but they just say, well, if that happens, it rains. So that's a simple, I mean, this today is still used in global forecast. In the French, the Germans and the English have a bit more sophisticated model, so they actually store moisture. They talk sort of, they have two types. I mean, they have sort of a cloud. They just have one that's droplets that below raindrop size and then above, and then it immediately falls to the ground. So you don't even model the fact that it takes time to get to the ground, right? So that's why rain is still a horrendously complicated or badly predicted thing, right? Because it's so coarse, the model they're using. And then on that scale, of course, it's very much filtered, right? I mean, the clouds are tremendously filtered. They don't even exist in some codes, right?
You hear a lot about this cascade of energy between scales in the weather models, and I mean, you haven't really discussed that in this context. So how does that come in? I mean, you're sort of filtering out.
Well, for large-scale circulation, for very large, I mean, in this semi-geostrophic limit, the motion is predominantly two-dimensional, and actually the cascade of energy doesn't happen. You have a cascade of vorticity. If you go to final scales, you have a cascade. I mean, it's three-dimensional. If you talk about truly three-dimensional dynamics, like convection, everything, which is more smaller scale, then you have a cascade of energy into the smaller scales, and then Darrell Holm would come in with Alpha Euler and all these sort of ideas, what you do, how to filter the energy that goes out of the system. So then it doesn't really make sense anymore to talk about Hamiltonian dynamics for the reduced model, because energy is actually leaking out into the degrees you're not resolving. So then, you have stochastic modeling, thermostating, whatever you wish you can bring into the picture at this stage. But for this very large scale motion, it's actually quite interesting that Hamiltonian dynamics makes sense even on a truncated level.
Would it be fair to say, if you would account for vertical motion, you have to talk about cascade of energies?
But yes, I think it would come in at the scale that's smaller than the scale we've been talking about here. I mean, I'm not an expert, so I mean, I can only reproduce what I filtered out of, this is reduced information I'm propagating here. So you should really talk to people like Mike Cullen or so. But my understanding is that for these very large scale, I mean, roughly speaking, that's what happens. Yeah.
An even simpler question. Were we talking here about weather forecasting or about climate prediction? Not the same thing, right?
Well, this is sort of, you wouldn't use the shallow water equations for predicting the weather, right? But it's a conceptual model to, for example, discuss frontogenesis. So developing of fronts. So that's weather. That's not climate, right? So
if anything, we were talking about weather and not about climate.
yeah, I put this up. The title I just made up because Ben got so excited when last week we were all climate and everyone, we were all sort of discussing climate. So I just said I have to bring this in here. I mean, this is actually of course, all this gonna save the planet and it makes, it will change everything. So don't.
Now
yes.
you've got the grant, you can sort of.
Right. So yeah. So no. I mean, this is.
Okay, thank you once more.